If you're enjoying these astronomy sleep stories, you can support the channel with a quick like and subscribe, and if you feel like it, drop a comment telling me what city or country you're listening from. I actually read those. Now lower your screen brightness, get comfortable, and let your mind slow down. Tonight, we're drifting through the story of Mars. Before there were maps, before there were stories, before there was even a word for planet, there was only motion, dust and heat and gravity, all turning together around a newborn sun. The early solar system wasn't calm like the night sky feels calm now. It was chaotic, crowded, and violent in a slow, patient way, where time is measured in impacts and the sound is written into stone. Imagine a wide disk of material circling the sun like mist around a lamp, grains bumping and sticking, then clumping, then growing, a process that feels gentle until you remember that every step is powered by collision. Pebbles become stones, stones become boulders, boulders become mountain-sized bodies, and then, after enough time, those bodies become worlds. Mars took shape farther from the sun than Earth did, where the light is weaker and the cold has more influence, and it grew quickly at first, sweeping up what it could from the leftover rubble, then slowing down as the neighborhood got cleaned out. It never became as massive as Earth, and that single fact echoes through the rest of its story. Because smaller worlds cool faster. And when a world cools faster, it loses its grip on the things that make a planet feel alive. Internal heat, protective magnetism, thick air, stable water. There was a time, long ago, when Mars probably had more going on under the surface than it does now. A warmer interior, more volcanic activity, maybe even a magnetic field that wrapped the planet in an invisible shield the way Earth's does today. That shield matters more than most people realize, because the sun is always blowing, an endless stream of charged particles called the solar wind, and if you don't have a strong magnetic field, that wind can slowly strip your upper atmosphere away. Not all at once, not dramatically but steadily, like something precious leaking out through a pinhole over millions of years. That's one of the most haunting parts of Mars. It may not have died in a single disaster. It may have faded. The sky that might have once been thicker thinned out, molecule by molecule, until the planet couldn't hold heat as well, couldn't keep liquid water stable on the surface for long, couldn't keep the kind of environment that feels familiar. And yet, even as Mars cooled and dried, it kept leaving behind evidence, quiet hints in its landscape that something different used to happen here. Mars is red because its surface is rich in iron, and iron, when it's exposed and reacts, becomes rust. And on Mars, the rust isn't just a stain, it's the dust itself, a fine powder that coats the planet the way flour coats a countertop. Rust becomes powder. Powder becomes dust. Dust becomes the skin of Mars. It gets lifted by winds and twisted into dust devils that wander across plains like living spirals, and sometimes those winds build into storms so large they can wrap around the entire planet, turning Mars into a blurred orange marble, as if it's trying to hide itself. Under that dust, though, the planet is layered like a book. You have basalt from old lava flows, cooled and cracked. You have impact craters pressed into the surface like fingerprints, each one a timestamp from a different era, some sharp-edged and young, some softened by time and buried under sediment. You have cliffs where layers stack like pages, some formed by volcanic ash, some by wind-blown sand, some by deposits left behind when water or ice shaped the ground and then vanished. Mars makes time visible because it doesn't have Earth's constant recycling, no active plate, tectonics the way we have, no oceans endlessly erasing and rewriting coastlines, no forests growing over everything. On Earth, the world is always repainting itself. On Mars, the paint dries and stays. That's why Mars feels like a memory you can walk through. There's a mountain there called Olympus Mons, the largest volcano in the solar system, towering so high and spreading so wide that on Earth it would dominate entire regions. It exists like that partly because Mars has lower gravity, and partly because the planet's geology allowed a volcano to keep building in the same spot for a very long time without the crust sliding away beneath it. And there's Valles Marineris, a canyon system so vast it sounds fake until you see it. A wound across the planet that stretches thousands of kilometers, deeper than anything of its kind on Earth, as if Mars split open and decided to leave the scar uncovered. These aren't just cool features. They're proof that Mars was once energetic, that it once had a planet's full range of motion. And then there's the question people always come back to, the one that keeps pulling us toward Mars like a magnet. Water. Mars today is cold and dry on the surface, but it holds water in other forms, ice in the polar caps, ice buried under soil, frost that can appear as temperatures swing through the night. And the shape of the land suggests that in the past, water didn't just exist, it moved. There are ancient valley networks that look like river systems, branching patterns that feel too organized to be random. There are delta-like shapes, fan deposits where something once flowed and slowed down and dropped what it carried. There are minerals that on Earth often form as the presence of water, salts and clays that hint at wet environments. Maybe lakes that lasted long enough for chemistry to happen slowly. You don't have to force the story into a perfect fairy tale. The truth is already interesting. Mars may have had periods where liquid water was possible, where the planet was warmer and wetter than it is now, where it held conditions that were at least closer to habitable than people expected. Then the planet shifted, atmosphere thinning, temperature dropping, water retreating into ice or underground, leaving behind dry channels like ghost footprints. It's a lonely kind of transformation, not an explosion, not a dramatic collapse, just a gradual turning of a world into a desert. Mars also has two small moons, Phobos and Deimos, irregular and dark like captured asteroids, and they move in ways that feel strange if you're used to Earth's moon. Phobos orbits so close and so fast that it rises in the west and sets in the east, racing across the sky like a thought that won't sit still. And it isn't stable forever. It's slowly spiraling inward, and one day it will either crash into Mars or tear apart into a ring. Even the companions of Mars are temporary. That's something space keeps, teaching over and over. Nothing is in a hurry, but nothing lasts. And still, despite the cold, despite the thin air, despite the dust and the distance, Mars has this pull on us, because for thousands of years it was a light in our sky that moved differently than the stars. Ancient people didn't see a rocky sphere. They saw a red wanderer, an ember traveling through the darkness, sometimes bright, sometimes faint, sometimes behaving strangely as it appeared to slow down and drift backward against the starfield, a trick of perspective that we now call retrograde motion. To early watchers, it felt like intention, It felt like a message. Different cultures gave it different meanings: war, fire, omen, God. But beneath all the myths was the same quiet behavior. Mars kept returning. It kept wandering. It kept being noticeable. And in a way, that's the most human part of this story. A person lying under a dark sky, no screens, no city glow, watching that red point and feeling something simple and honest: curiosity. Because Mars looks just familiar enough to tempt your imagination, but just alien enough to keep you wondering. It has seasons like Earth because it tilts, but its year is longer, stretching those seasons out, and its orbit is more eccentric, so its climate shifts unevenly. It has weather, but the atmosphere is so thin that even strong winds don't carry the same weight as they would here. A storm can look violent while feeling like almost nothing against a surface, except for the dust that gets everywhere, the dust that coats instruments and creeps into corners, the dust that turns the planet into a soft, rust-colored haze. It's a world of quiet extremes: freezing nights, pale daylight, storms made of powder, landscapes carved by forces that used to be stronger, and the long, slow silence of a planet that cooled too soon. So when we start the story of Mars, we're not starting with rockets or rovers or lab reports. We're starting with the oldest version of science there is: noticing. A red point that moves, a pattern that repeats, a mystery that refuses to stay small. Take a slow breath and let that red world drift behind your eyelids like a distant lantern. Because next we're going to give Mars its names, follow the myths across centuries, and then step into the moment humans finally leaned in closer with glass and lenses, and accidentally convinced themselves they saw something that wasn't there. For thousands of years, Mars was a red point that refused to stay still. It didn't sit in one place like the stars. It wandered, sometimes bright enough to pull your eyes away from everything else, sometimes faint enough to look like it was trying to disappear. And because humans can't stand a mystery that moves, we gave it meaning long before we gave it science. Different cultures looked up at the same ember and named it in their own language of fear and awe. The Romans called it Mars. The Greeks called it Ares. The Babylonians tied it to Nergal, linked with war and plague. In ancient China, it was the fire star, a thing you watched closely because it felt like it could announce trouble. Across time and geography, people kept circling the same idea. Red equals blood. Red equals danger. Red equals warning. But even when Mars was treated like an omen, it quietly became a tool, because the moment you track something, really track it, you're practicing the earliest form of science, even if you think you're doing prophecy. Watchers of the sky recorded where Mars rose and set, how its position shifted against constellations, how long it took to return, how its brightness swelled and faded. And Mars did something that made it impossible to ignore. It broke expectations. Most nights it drifted the way it should, slowly sliding eastward against the background stars. But at certain times it slowed down, stalled, and then appeared to move backward, tracing a strange loop in the sky before resuming its normal direction. Retrograde motion. To the ancient eye, it looked like a planet changing its mind, like a living thing hesitating, turning around and coming back. Early models tried to preserve perfection with complicated loops and nested circles, a sky machine built out of elegance and stubbornness. The real explanation is simpler and more peaceful. Earth and Mars both orbit the Sun, and sometimes Earth passes Mars, And when that happens, the geometry makes Mars appear to drift backward, the same way a slower car seems to slide in reverse when you pass it on the highway. But it took centuries for that explanation to feel acceptable, because the human mind likes to believe the heavens are centered on us. Mars kept pressuring those old beliefs simply by behaving honestly, because it wouldn't fit neatly into a perfect Earth-centered universe. It forced better math, it forced new models, it forced humility. Then telescopes arrived, and Mars stopped being just a point. It became a disk, a tiny coin of light with hints of surface. At first it was still vague, wobbly, limited by lenses, by atmosphere, by the eye itself. But it was enough to ignite the most dangerous ingredient in astronomy: partial information. The moment you can almost see something, you start finishing it with your imagination. Early observers began sketching what they saw: dark regions, bright regions, vague boundaries, shifting patterns that seemed to change across weeks and months. And then came the detail that lit a fuse in the human brain. Polar caps, bright white at the top and bottom, shrinking and growing with seasons. To a human mind raised on Earth, that felt familiar. That looked like ice. And if there's ice, then there's water. And if there's water, then maybe there are rivers. And once you say rivers, the next thought arrives on its own: life. Not proof, not evidence, just the seductive feeling that a distant world might be a cousin instead of a stranger. But Mars is a master of almost like Earth, but not quite. Mars has seasons because it tilts on its axis like Earth does, so sunlight shifts across hemispheres through the year. But a Martian year is longer, 687 Earth days, so the seasons stretch out, slow and drawn out, like the planet changes moods lazily. And Mars's orbit is more stretched than Earth's, meaning its distance from the Sun changes more dramatically through the year, so some seasons are harsher than others. The polar caps are not simply water ice. They include frozen carbon dioxide, dry ice, that can turn straight into gas as sunlight returns, meaning the poles can literally breathe in a way Earth's poles don't. When CO2 freezes out in winter, the atmosphere gets a little thinner. When it sublimates in spring, the atmosphere puffs back up. It's subtle, but it's real. The planet's air pressure rises and falls with the seasons like a slow tide. And the atmosphere, though thin, moves. Wind picks up dust. Dust hangs in the sky. Sometimes local storms become regional storms, and sometimes regional storms become global storms, wrapping the planet in a reddish veil. Early telescopes couldn't tell what was dust, what was shadow, what was real surface, and what was just the atmosphere smearing the picture. So Mars became a Rorschach test. Whatever you wanted it to be, you could squint and find a reason. Some thought the dark patches were oceans, others thought forests. Some claimed they saw seasonal darkening like vegetation blooming and fading with the weather. Others argued it was just dust being redistributed by wind, or just the way the eye interprets contrast at the edge of resolution. And all of it was happening while Mars itself played its own game. Every couple of years it comes close enough to Earth to appear larger and brighter in our sky. These close approaches, oppositions, became events. People waited for them, built better telescopes for them, drew new maps from them. When Mars is closer, the disk grows larger, details sharpen, and the urge to declare conclusions becomes unbearable. That's when the Canals era was born. In the late 1800s, an Italian astronomer described fine linear features on Mars using a word that could mean channels or grooves. The word was taken by many as canals, and that single interpretation changed everything. Because channel can be natural, canal sounds engineered. It sounds deliberate, it sounds like intelligence, it sounds like a civilization fighting to survive. And once you hand the public a hint of intelligent life, they don't politely wait for confirmation. They sprint. The idea took off. Mars is older than Earth, maybe drying out, maybe running out of water, and the inhabitants built a planet-wide system to transport meltwater from the poles to the equator. It's a story that hits every human weakness at once. The romance of a dying world, the drama of a desperate civilization, the thrill of not being alone. People drew maps filled with straight lines. They gave names to regions. They imagined cities. They imagined signals. They imagined a neighbor looking up at our planet and wondering the same things. One of the most famous promoters of this vision was an American astronomer who devoted years to observing Mars and popularizing the canal hypothesis, building an entire narrative of Martian engineering and seasonal behavior. And it wasn't just scientists. Newspapers ran with it. Public lectures packed rooms. Mars became entertainment and philosophy at the same time, a planet that acted like a mirror. What we believed about Mars revealed what we wanted to believe about ourselves. Even skeptics who doubted canals still argued about what the features could be, because the observations were inconsistent. Sometimes the lines appeared, sometimes they didn't. Sometimes they seemed doubled, parallel, like a strange geometry on the surface. Under worse seeing conditions, the brain tries to simplify messy detail into clean shapes, and straight lines are a classic illusion the human visual system creates when it's trying to make sense of tiny contrast differences. In other words, a lot of Mars in that era was actually the observer, but the belief persisted because it had momentum and because it was emotionally satisfying. It offered a story with stakes. It offered a universe that felt populated. It offered the kind of meaning humans always reach for late at night when the sky looks too big. The irony is that Mars was giving us real clues the entire time, clues that weren't as dramatic as canals, but were far more important. The polar caps really do change. The planet really does have seasons. The atmosphere really does carry dust. The surface really does have major regions with different reflectivity, dark basaltic plains, lighter dusty areas, bright polar frost. There are real features, real patterns, real physics. But the human mind, when it's hungry for certainty, often chooses the most exciting explanation over the most accurate one. And Mars made that easy because it sits right on the edge of what early telescopes could resolve, close enough to tempt, far enough to confuse. So for a while, Mars lived in two realities at once. In one reality, it was a real planet. Cold, dry, thin air, dust, rock, seasonal frost. In the other reality, it was a story world. Canals, cities, intelligence, survival. The second reality was louder because it was more fun. But the first reality was waiting, patient, like stone. And then, in the 20th century, the way we learn about Mars changed forever. We stopped relying on distant smudges and human interpretation and started sending machines, metal visitors that didn't get tired, didn't get hopeful, didn't fill gaps with imagination. The first flybys would return images that were shocking in their simplicity, and in one moment the canal world would collapse. Mars would become something else entirely, not a mirror for our fantasies, but a place, stark, real, and stranger than the dream. And that's where we go next, into the era of first contact, when Mars stops being a point and becomes a landscape. The canals that weren't there. Mars misread. If you want to understand how humans can fool themselves without meaning to, you don't need a magic trick. You only need a distant planet, a shaky telescope view, and a brain that hates uncertainty. Because Mars sits in a cruel, sweet spot. Close enough to show hints of detail, far enough to keep those details right at the edge of clarity. And when something is almost clear, your mind starts doing helpful work, connecting dots, smoothing noise, turning messy patches into clean shapes. That's what set the stage for the most famous misunderstanding in Martian history: the canals. In the late 1800s, astronomers were watching Mars during favorable oppositions, when Earth and Mars line up in a way that brings Mars relatively close and makes it appear larger in the sky. Better telescopes, more serious observing, more people mapping the planet like it was a new continent. They could see bright polar caps. They could see darker regions that seemed to shift with seasons, and they could see a few vague streaks and shadings across the disk. None of this was high definition. It was a small circle of light distorted by Earth's atmosphere, jittering and smearing with every ripple of warm and cold air above the telescope. Observers had to be patient. They had to stare for long stretches and wait for the brief moments when the image sharpened. And even then, what they saw was filtered through human expectation. An Italian astronomer, Giovanni Schiaparelli, published maps of Mars and used the word canali to describe linear features he believed he observed. In Italian, canali can mean channels, grooves, natural-looking pathways. It does not automatically mean artificial waterways built by engineers. But when the term reached English audiences, canali was widely translated as canals, and that one word carried a whole civilization inside it. Channel is geology. Canal is intelligence. Canal is planning. Canal is desperation and survival. Once that translation caught fire, the story wrote itself. Mars is old, Mars is drying out, and the Martians built a planet-spanning system to transport water from the poles to the thirsty equator. A dying world engineering its last chance. It was dramatic, it was poetic, and it was almost completely wrong. The biggest reason it spread isn't that people were stupid, it's that the observations were ambiguous and the idea was emotionally satisfying. Percival Lowell, an American astronomer, became the loudest champion of the canal narrative. He built an observatory largely to study Mars, and he didn't just report canals, he multiplied them. In his maps, the planet became a web of straight lines, intersections, and in some cases double canals, parallel tracks that seemed even more engineered. Lowell framed Mars as a place with purpose, with inhabitants, with intelligence facing extinction. The public ate it up. Newspapers loved it. Artists illustrated it. Lectures sold out. And soon, the canals weren't just a hypothesis. They were part of pop culture. The problem is that science doesn't care what makes a good story. If the canals were real, independent observers with different telescopes in different locations should consistently see the same network, the same lines, the same geometry. But that didn't happen. Some astronomers saw canals, others saw nothing but vague shading. Some saw a few lines one night and couldn't find them again on another. Maps didn't match. lines shifted or vanished. Observations changed with seeing conditions, the atmospheric steadiness over the telescope. And that is the giveaway right there. If a feature appears mostly when the image is unstable, you're probably looking at your own brain trying to force order out of blur. Human perception is not a camera, it's a prediction engine. When you stare at a low-contrast, partially resolved object, for long enough, your visual system starts simplifying. It loves edges, it loves straightness, it loves continuity. A few scattered dark patches can become a connected line in your mind, especially if you already suspect the line might exist. This effect is so strong that later experiments showed people can see linear features in intentionally blurred images even when no real lines are present, simply because the brain tries to interpret faint gradients as coherent shapes. Add fatigue, long hours at the eyepiece, the pressure of expectation, and the desire to be the one who figured it out, and you get an entire era of confident drawings of a planet that didn't exist. The other ingredient was Mars itself. Mars really does have dark and light regions. Some are rockier basaltic surfaces, some are dust-covered plains. Dust moves, storms redistribute it. Seasonal frost can brighten areas. So the planet's contrast patterns can change, which gave Canal supporters just enough real variability to keep their narrative alive. If a canal faded, they could claim vegetation along its banks was dying back. If a region darkened, they could claim growth. The story was flexible, and flexible stories don't die easily. But the canal hypothesis also did one important thing. It made Mars feel reachable. It turned a point of light into a world with stakes. It made people care enough to keep watching, to build better telescopes, to improve methods, and eventually to dream of visiting. Sometimes an incorrect idea still pushes the right kind of effort forward. Mars became the most emotionally loaded planet in the sky, not just a rock, but a possible neighbor. The tension between Mars as real geology and Mars as intelligent civilization simmered for decades, and the only way to resolve it was to stop guessing from a distance. Eventually, the 20th century delivered the tool that telescopes could never be: spacecraft. When the first probes flew past Mars, they brought back images that didn't depend on a tired human eye interpreting a shimmering disk. They brought back photographs, and those early photographs were brutal in the simplest way. They showed craters, lots of craters, a surface that looked, in many places, more like the moon than like Earth. No neat grid of canals, no straight lines carved across continents, no obvious signs of a global engineering project. For a lot of people, it felt like a disappointment, because the dream was prettier than the truth. But the truth had its own beauty, one that takes a different kind of patience. The truth was that Mars is not a stage designed for our fantasies. It's a planet with its own history. Violent impacts, giant volcanoes, vast canyons, ancient floods, long droughts, and a climate that changed over billions of years. The canals were mostly a lesson. When you want something badly enough, your mind will offer it to you, even if the universe never did. And yet, in a strange way, the canal era didn't end curiosity. It sharpened it. Because once the civilization story collapsed, the real question became even more haunting. If Mars is not covered in canals and cities, what happened to it? Why does it look like a world that almost had the ingredients of habitability, but ended up cold and thin and dry? Did it ever have stable lakes, rivers, maybe even oceans? If it did, where did they go? Did anything ever live there, not as a civilization, but as something microscopic and quiet? And if life never started, why not? Those questions are less dramatic than canals, but they are deeper, and they're exactly why Mars became the target of landers, rovers, orbiters, and decades of study. So the canals were a mistake, but they were also a turning point. They revealed how badly humans wanted Mars to be alive, and they set the emotional groundwork for exploration. Because once you care, you build ships. And once you build ships, you stop arguing about smudges in a telescope and start touching the dirt. Next, we move into the first true visitors, when Mars becomes more than a story in our heads and turns into a place with horizons, rocks, and real images sent home through the dark. After the Canal era, Mars didn't become less interesting. It became more honest. The fantasies faded, and what replaced them wasn't emptiness, but a new kind of curiosity. If Mars isn't a world of engineered waterways and hidden cities, then what is it really, and what happened to it over time? For centuries we were stuck at the shoreline of distance, staring through air that wobbled the view and letting our minds do the rest. Then, in the 20th century, the distance itself began to shrink. Not because Mars moved closer, but because we finally built machines that could cross the space between worlds. The first visitors weren't rovers crawling across red soil. They were quick, quiet flybys, metal messengers rushing past a planet they couldn't yet touch, taking fast snapshots like someone peeking through a doorway. When Mariner 4 flew past Mars in 1965, it sent back the first close-up images of another planet's surface, and the result was startling in its simplicity. Craters. A surface pocked and scarred, ancient-looking, more like the moon than like a second Earth. For the dreamers who wanted seas and forests, it felt like a cold splash of reality. But for science, it was a beginning. Those first images were few, grainy by today's standards, and covering only a small portion of the planet. But they were something no telescope could compete with. Proof. Proof that Mars was not going to be understood by guessing. Proof that the planet had a history written into its rocks. And from that moment, the story of Mars split into two tracks that would keep weaving together. Disappointment for the myth and excitement for the truth. Soon more Mariners followed. Mariner 6 and 7 in 1969 returned additional images, more context, more surface. Then Mariner 9 arrived in 1971 and changed everything again, not with a flyby, but as the first spacecraft to orbit another planet. It was meant to map Mars in detail, to see the world systematically, to turn it from a mystery into geography. But when Mariner 9 got there, Mars greeted it with a kind of dry drama, a global dust storm. The planet was wrapped in haze, as if it had decided to hide itself at the exact moment we arrived. For weeks, the cameras saw very little, just a pale blur and hints of darker forms beneath. And then, as the dust began to settle, the features emerged like slow silhouettes. Volcanoes, not just volcanoes, giants, canyon systems, not just canyons, vast wounds, ancient channels that looked like something had once flowed, layered terrain, polar landscapes. Mariner 9 revealed Mars as a planet of extremes, a place that had once been more energetic than the cratered images alone suggested. It was as if we had walked into a quiet room and realized the furniture was far larger than expected. Olympus Mons appeared as a colossal volcanic shield, so wide it seems to belong on a different kind of world. Valles Marineris cut across the planet like a massive scar, a canyon system stretching thousands of kilometers, deeper and broader than anything Earth offers in a single sweep. And then there were the channels, some branching like river networks, others carved like enormous flood paths. Features that didn't scream canals, but whispered something more interesting. Water shaped this planet at some point, and it did so on a scale that demanded attention. Orbiters could map, but they couldn't taste the dirt. If you want to understand a world, you eventually want to touch it, to sample it, to feel how it behaves up close. That's where Viking comes in, and if the earlier missions were like distant glimpses, Viking was like finally stepping onto the porch. In 1976, NASA's Viking program delivered 2 landers to the Martian surface, each paired with an orbiter, and the goal was blunt and beautiful. Study Mars as a real environment and search for signs of life. When Viking 1 touched down in July, and Viking 2 followed later, the images they returned felt almost quiet. A rocky plain, a pinkish sky, a horizon that looked both familiar and completely wrong. The surface was covered in boulders and smaller rocks, scattered like a field that had been tossed and left. There were no trees, no rivers, no movement besides the wind. If you listened to the mood of those first panoramas, Mars wasn't a bustling world. It was a desert holding its breath. But even in that stillness, there was so much to learn. Viking measured temperature swings that could make your head spin. Cold days, colder nights, and a thin atmosphere that doesn't buffer change the way Earth's does. It confirmed the atmosphere was mostly carbon dioxide, with very little oxygen and water vapor, and the pressure at the surface was so low that liquid water, under typical conditions, can't persist for long. It would boil or freeze quickly, skipping the comfortable middle state that Earth takes for granted. Viking watched the sky, tracked dust, and studied the behavior of the soil. And then there were the life detection experiments, the part people still argue about in documentaries, because Viking's results were the kind that don't give you closure. The landers carried tests designed to detect biological activity in the soil. One experiment, the labeled release test, produced a result that looked, at first glance, like something living might do. When nutrients were added to the soil, a release of gas was detected, suggesting some kind of reaction. But other experiments didn't find clear organic molecules the way many expected they would if life were present. The chemistry of Mars turned out to be tricky because the soil isn't inert. It's reactive. Later research would suggest Mars's surface chemistry includes oxidizing compounds, substances that can break down organics and mimic some patterns you might associate with biology. So Viking left us with a strange kind of legacy. Hints that were exciting and explanations that were sobering. Not proof of life, not proof of no life. Just the uncomfortable middle where Mars sits often, tempting you with possibilities while refusing to make it easy. And yet, Viking was a triumph in a deeper way. It didn't just look at Mars, it turned Mars into a place we could describe with numbers and images and direct measurements. It anchored our imagination to reality. It proved we could land there, operate there, and learn there. It showed that Mars is not a blank red dot. It's a planet with weather, soil, seasons, and a history more complicated than dead rock. The canyon systems and volcanoes suggested a planet that once had internal energy and geological ambition. The channels suggested a planet that once had flowing water, at least episodically, and possibly lakes and seas in its distant past. The thin air and cold surface explained why Mars looks the way it does today, and why it feels so quiet in the lander images. This is a world where the environment doesn't nurture surface life easily, where the sky is too thin to hold warmth, where water is mostly locked away as ice or hidden underground. Viking also did something subtle to the human mind. Before Viking, Mars was either myth or a distant target. After Viking, Mars became intimate, a horizon line, a rock you could point to, a sky color you could name. It stopped being a symbol and became a landscape. And landscapes invite questions that symbols don't. What is that rock made of? How old is this ground? Why is the soil so reactive? Where did the water go? Could something survive below the surface, protected from radiation, protected from the harsh chemistry, protected from the thin, dry air? Could there be ancient biosignatures locked in clay deposits or sediment layers, preserved the way fossils can be preserved on Earth, waiting for the right rover with the right drill? The first visitors didn't answer everything, but they changed the entire tone of the story. They took Mars from a planet we argued about to a planet we investigated. And in a way, they also taught patience, because Mars doesn't reveal itself quickly. It reveals itself in layers, like the planet itself. One mission shows you craters and tells you the surface is old. Another shows you volcanoes and tells you the planet once ran hot. Another shows you channels and tells you water once moved. Another lands and tells you the soil reacts in strange ways and the air is thin and the cold is real. Piece by piece, Mars becomes clearer, not as a dream of civilization, but as a world with a long, quiet biography. So as you settle deeper into rest, you can picture that first Martian sunrise seen by Viking, a dim sun in a dusty sky, light spreading over stones that haven't been touched by anything alive that we know of for a very long time. A calm, empty plain, not sad, just vast. The kind of place that makes you feel how big time is, and the kind of place that makes you understand why we kept going back. Because once you've seen another world from its own surface, even briefly, you don't stop wondering what else is hidden there. Mars looks simple from far away. A red disk, a quiet desert. But when you start paying attention, it's not one story. It's many stories stacked on top of each other, written in different kinds of stone. Part of what makes Mars so easy to fall asleep to is that it moves slowly. Nothing rushes there. Even its biggest events, storms that can cover the planet, build over time like a deep breath. And the land itself feels like a calm museum of ancient forces. Volcanoes that stopped speaking long ago, canyons that hold shadows like memory, plains that look still but were once shaped by fire, impacts, and floods. To understand Mars as a real place, you don't start with the headlines. You start with the body, what it's made of, how it formed, and what the surface is trying to tell you. Mars is a rocky planet, like Earth, built from silicates and metals, but it's smaller, about half Earth's diameter, and that size difference changes everything. Less gravity, less internal pressure, faster cooling, a shorter window for the deep internal engine that drives volcanism and magnetic fields. On Earth, the planet's interior stays hot for a long time, and the crust is constantly being recycled by plate tectonics. The surface is restless. Continents drift. Oceans swallow and reveal land. Mountains rise and erode, then rise again. Mars doesn't have that same constant reset. It's more like a planet that did most of its loud work early, then gradually quieted down, leaving its surface to sit and age in the open. That's why so much of Mars is ancient. It's also why Mars is an incredible archive. If something happened there billions of years ago, there's a chance it's still written into the landscape. Much of the Martian crust is basaltic, formed from volcanic activity, lava that cooled into dark rock. Those basaltic plains are some of the planet's broadest features, and in places they're covered by dust that can hide their darker tone. When you look at Mars's surface, you're often seeing a mix, the bedrock underneath and the dust veneer above. The dust itself is not just loose dirt, it's chemically meaningful. It's iron-rich, oxidized, and extremely fine, and it can be moved easily by wind in a thin atmosphere because Mars has lower gravity, and because dust particles are so small they can stay suspended longer. Mars is a world where the air is thin, but the dust is persistent, and that dust can make the same region look different from year to year as it's redistributed. Beneath the dust, the planet divides into regions that feel like different chapters. There are older, heavily cratered highlands, especially in the southern hemisphere, where the surface has been sitting exposed for a very long time. Craters overlap craters there, like scars layered over scars. That heaviness tells you those terrains have been around since the early solar system's more violent days, when impacts were more frequent. Then there are younger, smoother plains, many in the northern hemisphere, where the crater count is lower, suggesting these surfaces were meaningfully resurfaced later, by lava flows, by sediment deposition, by processes that erased older scars. The north-south contrast is one of Mars' biggest mysteries. The northern hemisphere sits lower on average than the southern highlands, and that difference, called the Martian dichotomy, could be the result of ancient impacts, internal processes, or some combination of both. It's as if the planet has two faces, one older and rougher, one younger and smoother. And then there are the giants. Olympus Mons isn't just a big volcano. It's a clue about how Mars works. On Earth, volcanoes like those in Hawaii form over hotspots, but as tectonic plates move, the volcano gets carried away and new ones form, creating chains. Mars doesn't have the same plate motion, so if a hotspot stayed active under one region for long enough, the volcano could build and build and build, stacking lava flows over millions of years until it became something enormous. Olympus Mons is broad and gently sloped, a shield volcano like a colossal dome, with an outer escarpment and a summit caldera complex, collapsed depressions where magma chambers once emptied. Because gravity is lower, the volcano can grow taller before its own weight becomes unstable. Because the crust isn't moving, it can stay centered over its heat source longer. The result is a mountain so huge it changes the idea of what mountain means. Nearby, the Tharsis region holds other massive volcanoes too, an entire volcanic plateau that suggests Mars once had internal power concentrated in certain regions, enough to reshape the planet's crust. Tharsis itself is so large it likely influenced the planet's stress patterns, and those stress patterns may connect to another feature that feels almost unreal: Valles Marineris. Valles Marineris is a canyon system stretching thousands of kilometers, a network of chasms that can be several kilometers deep. It isn't just one crack. It's a complex set of troughs and collapsed regions. One leading idea is that it formed largely from tectonic stretching, Mars' crust being pulled and fractured as the Tharsis region rose and loaded the crust, creating stress that tore the surface open. Over time, landslides and erosion widened and modified the canyon walls. The point isn't just how big it is, it's what it implies. Mars has had major crustal forces, and those forces were strong enough to split the planet's surface in a way that still dominates maps today. And then, scattered through this volcanic and tectonic story, there are signs of water, or at least signs of something that behaved like water. Some channels on Mars look like branching river networks, carved over time by flowing liquid. Others look like outflow channels, massive flood features carved quickly by catastrophic releases of water. Ashket were released in enormous volumes, ripping across the landscape and leaving broad, scoured paths behind. There are also features like alluvial fans, delta-shaped deposits, and layered sedimentary rocks that suggest water once transported material and laid it down in calmer environments. Mars is strange because it holds both styles of evidence, gentle and catastrophic. Slow carving that suggests repeated flow, and giant channels that suggest sudden outbursts. That mix hints at a planet whose water history wasn't stable and constant like Earth's, but episodic. Periods of wetter conditions, periods of freezing, moments of release, long stretches of dryness. Another major ingredient in the surface story is ice. Mars' polar caps are among its most visible features, and they're layered like a cake, stacked deposits that record climate change over time. The poles hold water ice and carbon dioxide ice, and the polar layered deposits suggest cycles of accumulation and loss tied to changes in the planet's orbit and tilt over long timescales. Mars's tilt can change more dramatically than Earth's because it lacks a large, stabilizing moon like ours. Those tilt variations can shift where sunlight falls, which shifts where ice is stable, which shifts where frost accumulates. Over hundreds of thousands to millions of years, the planet's climate can reorganize itself, moving ice from poles to mid-latitudes and back again. That's why there's evidence of buried ice in places far from the poles, subsurface ice that sits like a frozen reserve, protected under soil. The surface, then, is not just rock and dust. It's rock, dust, and hidden ice, and that combination shapes how Mars behaves even today. When you look at Mars, you also see the work of impacts. In some ways, Mars is a museum of collisions. Because it has less atmosphere than Earth, fewer incoming objects burn up or break apart. And because it has less erosion and no oceans, craters can remain visible for billions of years. Craters are not just scars, they're clocks. The more craters you count on a terrain, the older it likely is. By comparing crater densities across regions, scientists can estimate relative ages. Older highlands, younger plains, resurfaced volcanic regions, sediment-filled basins. It's a quiet way of reading time. And there's another quiet force that shapes Mars. Wind. On Earth, wind shapes sand dunes too, but on Mars the dunes feel otherworldly because the atmosphere is thinner and the gravity is lower, changing how grains move and how dunes form. Mars has Martian dunes, star dunes, long ridges, wave-like fields that stretch for kilometers. It has dust devils, tall spinning columns that can sweep across the surface and leave dark tracks where they temporarily clean dust off the ground. Sometimes a dust devil is like a little eraser, drawing patterns across a plane. Sometimes it's like a little painter, lifting dust and spreading it elsewhere. Over time, wind reshapes the surface in subtle, constant ways, even in a thin atmosphere, because Mars is patient and time is long. So the Martian surface isn't one thing. It's ancient highlands and younger plains. It's huge volcanoes built in place over eons. It's a canyon system born from stretched crust and modified by collapse. It's craters that act like timestamps. It's channels that hint at water, sometimes gentle, sometimes catastrophic. It's polar layers recording climate cycles. It's dust and wind forever rearranging the surface like slow breath. And it's all happening under a sky that doesn't protect the ground the way Earth's does. Mars has little shielding from radiation. The surface is bombarded by cosmic rays and solar particles, which matters not just for future humans, but for the preservation of organics. If life ever existed, or if complex organic molecules ever formed, the best place to look for preserved traces might be below the surface, in sediment, layers, in clay deposits, in places where rock and soil can act like a protective blanket against the harsh sky. That's why modern missions focus so much on ancient lakebeds, sedimentary formations, and places where water once collected and deposited layers. Because layers preserve, layers remember, and Mars, more than almost any other nearby world, is a planet that remembers. So as you settle deeper into sleep, you can picture the surface as a quiet library. Pages of basalt and dust, chapters of volcano and canyon, footnotes written in craters and hidden lines of ice beneath the soil. Nothing is rushing there now. The biggest mountains are still. The deepest canyons hold the same shadows. The dunes shift grain by grain in a slow motion that feels almost like breathing. And the planet keeps circling the sun, year after long year, letting its surface hold the story in silence, waiting for the next visitor to arrive and read another page. The ghost that won't leave Mars is dry enough to look finished, like a world that has already decided what it is. And yet water keeps showing up in the story anyway, not loudly, not as a blue ocean under a bright sky, but as evidence, as residue, as shapes carved into rock, as minerals that only make sense if liquid once lingered. If Mars is a quiet planet, then water is the quietest character in it, never fully present, never fully gone, always hinted at, always pulling you back. The first clues are written in the land itself, valley networks that branch like river systems, patterns that resemble drainage basins, channels that twist and split the way flowing water naturally does when it obeys gravity and terrain. Some of these valleys look old, softened by time, like they've been sitting exposed for billions of years, and that age matters because it suggests Mars may have had a much wetter phase early on, when the planet was warmer, when the atmosphere may have been thicker, when liquid water could exist for longer stretches instead of flashing into vapor or freezing instantly. Then there are the outflow channels, the huge ones, carved as if a dam broke on a planetary scale. Broad scoured pathways, streamlined islands, features that look like they were shaped quickly by catastrophic floods. Those floods don't necessarily require a warm, rainy Mars the way people imagine it. They could come from underground reservoirs released suddenly, from pressurized aquifers, from ice melted by volcanic heat or impacts, from moments when the planet's hidden water escaped in a rush. Mars seems to tell two water stories at once, one slow and persistent enough to carve branching networks, and another sudden and violent enough to gouge enormous channels like a wound. And if you follow those channels, you start to find basins, lowlands, places where water would naturally collect. And that's where the next kind of evidence appears. Deltas and lakebeds, fan-shaped, deposits where flowing water slowed down and dropped sediments, building layers the way rivers build deltas on Earth. A delta is hard to fake because it implies sustained flow into standing water, not just a brief flood. It suggests a lake that lasted long enough to receive sediment and organize it into structure. And structure is what water loves to create. Mars has places where ancient craters appear to have held lakes, where inlet channels bring material in and the basin holds it, where layered sedimentary rocks stack up like calm years passing one by one. Those layers are important not only for the water story but for the life story, because on Earth, calm water environments are good at preserving things, burying organics, protecting fragile traces under sediment. That's why so much attention has gone into ancient lake regions on Mars. If Mars ever had microbial life, those are the kinds of places that could have kept its signature long after the organism itself disappeared. But Mars doesn't just show water in shapes, it shows water in chemistry. Certain minerals form more easily when water is involved, especially over time. Clays, for example, often indicate prolonged interaction between rock and liquid water, a slow alteration that implies stable or repeated wet conditions. Sulfates can indicate evaporation, water coming and going, leaving salts behind. Salts in general are a big deal, because salts can form when water dissolves minerals and then evaporates, concentrating what it carried. Mars has salty deposits that look like the remains of ancient brines, and those brines matter because salty water can stay liquid at lower temperatures than pure water can. On Mars, where cold dominates, brines are one of the few plausible ways liquid water could exist even briefly on or near the surface today. The water story changes with time. Early Mars might have had rainfall, rivers, lakes, maybe even something like a northern ocean in lowlands. Still debated, still complicated, but not ridiculous when you consider how different the planet may have been billions of years ago. Later Mars becomes colder, drier, and thinner-aired, and the water retreats. Some escapes to space over immense time, some freezes into polar caps, some becomes ground ice locked beneath dust and rock, and some may remain as deeper subsurface reservoirs, protected from surface radiation and extreme temperature swings. The poles are the most obvious modern water storage. Mars's polar caps include water ice, layered with seasonal carbon dioxide frost, and the layers themselves act like a climate record, built over long cycles as the planet's tilt and orbit change. Mars doesn't have a big stabilizing moon like Earth, so its tilt can shift more dramatically over geologic time, and when tilt shifts, sunlight shifts, and when sunlight shifts, where ice is stable shifts. That means Mars can move its ice around over long ages, building layers at the poles, then relocating ice toward mid-latitudes, then pulling it back again, like a slow migration of frozen reserves. Evidence for widespread subsurface ice isn't just theoretical. Landers and orbiters have found signs that beneath the dust, there are places where ice is surprisingly close to the surface. Sometimes you can even see fresh craters exposing bright material that looks like ice before it sublimates away. There are also polygonal patterns in the ground in certain regions, cracking patterns that resemble permafrost terrains on Earth, where ice in the soil expands and contracts with temperature changes, slowly reshaping the surface into geometry. So Mars today can be thought of as a planet with hidden water, not flowing rivers, but frozen stores underfoot, quiet and stubborn. And then there are the more controversial, more tantalizing hints, features like gullies on crater walls that look like they were carved by something flowing downhill. At first glance, gullies scream water because on Earth gullies are often shaped by liquid runoff. But on Mars, the story is trickier. Some gullies could form from dry flows of dust and sand, triggered by seasonal frost or sudden collapses, behaving like avalanches. Some may involve brines in certain conditions. Some may involve carbon dioxide ice processes, slabs of dry ice sublimating and lubricating flows that carve channels without liquid water at all. Mars loves to keep the answer just out of reach. The shape is familiar, the mechanism is alien. For a while there was also excitement over recurring slope lineae, dark streaks that appeared seasonally on slopes and faded later, which some interpreted as salty water flows. Later analysis suggested many of these could be dry granular flows triggered by temperature changes or dust movement, not necessarily liquid water. The point isn't that scientists can't decide. The point is that Mars makes the distinction difficult because its surface processes are unfamiliar combinations. Dust, frost, thin air, low pressure, cold, and long time. It produces features that look like water because water once mattered there, but it also produces lookalikes through other physics that Earth doesn't showcase as often. Still, even if you strip away every modern, maybe liquid claim and stick only to what feels solid, Mars remains a planet with a deep water past and a water present that's mostly locked away. And that water past is not small. The planet is carved, it's etched, it's layered, it's chemically altered. Those are not the signatures of a world that never had water. Those are the signatures of a world that had water and then lost the easy version of it. That loss is part of what makes Mars feel haunting. It's like walking through the remains of a river town that dried up, channels still there, stones still shaped, but the flow gone. You can almost hear what it used to sound like if you let your mind fill in the silence. Imagine an ancient Martian morning, billions of years ago when the sky was thicker, when the sun rose through haze, when water collected in basins and moved downhill, carrying sediment, smoothing rock edges, laying down layers that would later become stone. Imagine lakes with shorelines, not necessarily blue and warm, but present. Cold lakes, briny lakes, shallow lakes that froze and thawed, yet still persisted long enough to matter. Then imagine the slow shift, atmosphere thinning over time, the planet cooling, the stable liquid vanishing, the surface turning into a place where water can exist but can't stay, where it becomes ice and hides, where it becomes vapor and escapes, where it becomes salt-stained memory. The water didn't just disappear, it changed form and location. It moved from visible to hidden. And because it's hidden, it becomes a question again. If there is ice under the soil, could there be pockets where heat or pressure creates brief liquid environments? If brines can form, could they exist long enough for chemistry to happen? If water once sat in lakes and rivers, did it ever carry life with it? Microscopic life that left traces in clay and sediment? The water story turns into the habitability story without you even forcing it, because water is the universal solvent of biology as we understand it, and even when Mars is dry, The evidence of water keeps whispering that the planet used to be more forgiving. That whisper is why rovers drill into rocks, why orbiters scan for minerals, why scientists obsess over ancient shorelines and layered deposits, why the search isn't just for water itself, but for what water would have left behind. On Mars, water is not the main character in the present, but it is the main author of the past. It wrote the channels, it built the deltas, it altered the minerals, it laid down the layers, and even now it sits frozen in caps and buried ground ice, waiting in darkness. And if you're listening to this while the room is dim and your eyes are heavy, that's a good place to let your mind rest. A planet that once moved with water, now quiet, still holding it in hidden places like a secret it never fully let go of. The question that won't let Mars be quiet. If water is the ghost that won't leave Mars, then life is the question that won't let the story end. Because once you accept that Mars may have been wetter long ago, once you accept that rivers carved valleys, that lakes may have filled craters, that minerals formed in the presence of water, the next thought arrives almost automatically. If Mars ever had the right conditions, did anything ever live there? Not cities, not canals, nothing dramatic, something microscopic, something quiet, something that could exist without being seen, the way most life on Earth existed for most of Earth's history. When people think life, they picture animals and plants. Mars forces you to think smaller, slower, simpler. Life as chemistry that learned how to copy itself. Life as a tiny system that takes energy from its environment and turns it into persistence. That's the kind of life Mars could have hosted if it hosted any at all, and that's why the search for life on Mars is less like hunting a monster and more like reading a faint signature on an ancient page. The first big modern attempt to answer the question wasn't poetic, it was mechanical. Viking. 2 landers. Experiments designed to detect biological activity in soil. One of Viking's tests produced a result that startled people. When nutrients were added to a soil sample, the system detected a release of gas that looked like metabolism. It looked like something alive had eaten and breathed something out. But another set of instruments failed to detect organic molecules as clearly as expected, and in the decades since, the likely explanation has leaned toward chemistry rather than biology. Mars's soil appears to be highly reactive, containing oxidizing compounds that can break down organics and create gas-releasing reactions that mimic what life might do. That's the Viking legacy in a single sentence, a hint that excited the world, wrapped in ambiguity that never fully went away. It was a reminder that Mars is not just cold and dry, it's chemically tricky. And it taught scientists a painful lesson. On Mars, you don't just look for life. You look for life's fingerprints, and you also look for all the non-living processes that can forge similar fingerprints. That's what makes the search hard. Not impossible, just demanding. Another complication is radiation. Mars doesn't have a thick atmosphere or a strong global magnetic field shielding its surface the way Earth does. Over long periods, cosmic rays and solar radiation can bombard the surface, breaking down complex molecules. If organic compounds were once present on the surface, they may not survive there for billions of years. That means the best place to look for ancient biosignatures isn't necessarily on the open ground. It's in protected locations, buried sediment layers, clay-rich deposits, rocks that formed in water, places where fine-grained minerals can trap and shield organics, and especially below the surface, where radiation is weaker. If Mars ever had life, the surface today is probably not the easiest place for it to leave a clean record. So the search shifted from, "Is there life here right now?" to a, "Was there life here long ago, and can we still find traces?" That shift is one reason modern missions focus so heavily on ancient lake beds and sedimentary rocks. Sediments are like time capsules. On Earth, some of the best fossil records come from sediments laid down in calm water, lakes, shallow seas, river deltas, places where fine particles settle, burying whatever is there and protecting it from oxidation and radiation. Mars has ancient lake beds that look like they once held water long enough to build layered deposits, and those layers are exactly what you'd choose if you were trying to preserve delicate chemistry for billions of years. The goal becomes less about finding a living organism and more about finding patterns that are difficult for geology to fake, certain distributions of organic molecules, certain isotopic ratios, certain textures in rocks that resemble microbial mats, certain mineral associations that suggest biological processing. That's why the Mars life search is patient. It's slow. It's careful. It's a forensic investigation carried out across a planet. Some missions have found organic molecules, or at least carbon-bearing compounds, in Martian rocks and soil. That alone doesn't mean life, because organics can form without biology. They can come from meteorites. They can be made by chemical reactions. But their presence is still meaningful, because it shows Mars can preserve at least some organic material under the right conditions, and it shows the ingredients of life, carbon chemistry, water history, energy sources, have existed there in some combination. Another recurring mystery is methane. Methane on Earth is often associated with biological activity because microbes can produce it, but methane can also be produced by non-biological processes, including certain water-rock reactions in the crust. On Mars, methane detections have been reported intermittently. Plumes, seasonal patterns, spikes, and the debate is intense because the atmosphere is thin and methane should break down over time. If methane is present, something must be making it relatively recently, or it must be stored and released. But the detections are inconsistent across instruments and missions, and that inconsistency makes the story messy. Still, even the messy story is interesting. It suggests Mars may be chemically active in ways we don't fully understand, and it keeps the door cracked open for the possibility of subsurface environments where reactions happen and gases can accumulate. If you want a calm way to think about it, imagine Mars as a planet with an underground world we haven't fully seen. The surface is harsh. Thin air, radiation, cold, reactive dust. But below, the surface, conditions can be more stable. Temperatures increase with depth. Radiation drops off. Ice can exist protected from sunlight. Brines can potentially form. There could be pockets where water and rock interact, producing energy-rich chemical gradients that microbes on Earth would love. On our own planet, life exists in places that used to sound impossible. Deep underground, in rock fractures, in hydrothermal systems, in Antarctic ice, in the most acidic or salty environments you can imagine. Earth taught us that life is not fragile in the way people once believed. It's stubborn, adaptable, and creative with chemistry. That lesson doesn't prove life exists on Mars, but it does expand what possible means. If Mars ever had life, it might not have needed a warm ocean and blue skies. It might have lived in briny water under ice, in sediments at the bottom of a lake, in pores of rock, in underground pockets protected from the worst of the surface. And if it never had life, that absence is still a powerful scientific result, because it would mean even with water and chemistry and time, life is not guaranteed. That would tell us something enormous about the universe. That habitability is not the same as inhabited. That the line between a world that could host life and a world that actually does may be thinner and more complicated than we want it to be. That's why Mars matters so much. It's close enough to investigate in detail, but different enough to be a real test case. Mars is the nearest world that might have been habitable long ago, and if we can read its history properly, it can help answer questions bigger than Mars itself. How often does life start? How fragile is it in the face of planetary change? Does it need Earth-like stability, or can it arise in colder, harsher cycles? If life started on Mars and died, what killed it? If life never started, what was missing? Energy? Stability? Time? Protection? And if life started and still exists somewhere below, quiet and hidden, what does that say about how common life might be on other worlds? The search for life on Mars, then, isn't just a hunt. It's a mirror held up to our own planet's story. Earth stayed warm. Earth kept a thick atmosphere. Earth kept oceans. Earth kept a magnetic shield. Mars may have lost some of those protections early. Mars may have dried and cooled faster. Mars may have had a shorter window where the surface was friendly. That difference between Earth and Mars is like a natural experiment. Two neighboring worlds formed from similar ingredients, then diverged. One became a living planet. One became a quiet desert with ice and dust and ancient channels. When you listen to the story of Mars at night, that divergence is part of what makes it calming and heavy at the same time. It reminds you that planets change and that time doesn't care about comfort. And still, the question remains open enough to keep drawing us back. Somewhere, in those layers, somewhere in those clays, somewhere below the cold surface, is there a signature of life, ancient or present, faint but real? Or is Mars a lesson in how close a world can get and still remain empty? Either answer is profound. Either answer changes how we see the universe. And until we have the final evidence, samples returned to Earth, deeper drills, clearer biosignature tests, the story stays suspended in that quiet tension, the kind that doesn't keep you awake, but keeps your mind gently curious as it drifts toward sleep. The long goodbye and the quiet future of Mars. By now, Mars doesn't need to be dramatic to feel important. It's already done what it needed to do. It pulled us in with myths, confused us with near visions, humbled us with reality, and then kept rewarding us with deeper layers the closer we looked. Mars went from a red omen to a possible neighbor, from imagined canals to real volcanoes and canyons, from a fantasy of civilization to a real planet with a complicated past. Fire, ice, floods, dust, and time. And when you step back and hold the whole story at once, the most honest description of Mars is simple. It's a world that almost feels familiar, but not enough to let you relax. And that almost is what makes it so magnetic. Mars has shown us that a planet can have the ingredients for habitability, water history, carbon chemistry, energy sources, and still become harsh. It has shown us how much a thick atmosphere matters, how much a magnetic field matters, how much size matters. Earth and Mars formed from similar raw materials in the same neighborhood of the solar system, and yet they diverged into two different destinies. Earth stayed warm and wet and protected. Mars cooled faster, lost more air, and turned surface water into ice and memory. That divergence doesn't feel like a moral lesson, it feels like physics, and physics has a calming honesty to it. Things change because forces act, and time is long enough for small changes to become total transformations. That's why Mars is such a powerful planet to study. It's close enough to investigate, but different enough to teach. If we ever find that Mars once hosted microbial life, even briefly, it would mean life is eager, able to ignite in more than one place when conditions allow. It would hint that the universe may be filled with worlds where life began, even if it didn't always survive. And if we find Mars never had life despite water and chemistry, that would be just as important because it would mean life is rarer than we hope, or it requires a combination of stability and timing that Mars didn't have. Either way, Mars helps us refine what possible really means. And that's the scientific heart of the planet. Mars is a test case for life, for climate, for planetary change. It's a nearby example of a world that might have had a window of gentleness and then lost it. And while the big questions pull the headlines, life, oceans, colonization, the day-to-day reality of Mars is still quiet. A thin sky breathing seasonally as carbon dioxide freezes and sublimates at the poles, dust lifting into storms that can wrap the planet in a veil, frost appearing and vanishing, dunes shifting grain by grain, shadows moving slowly across ancient rock. The planet is active in subtle ways. It isn't dead so much as settled. That's why robots do so well there. They can wait. They can measure. They can take their time. And Mars has become a planet we don't just visit. Once, we keep returning. Orbiters mapping from above, rovers crawling and drilling, landers measuring tremors, cameras watching the sky change color at sunset. Every mission is a new set of sensors. Every mission adds a new layer to the biography. And the longer we stay curious, the clearer it becomes that Mars is not one answer. It's a collection of answers across time. Its early warmth, then cooling. Its water shaping rock, then water retreating into ice. Its big volcanism, then quiet. It's a thicker atmosphere long ago, then a thin one now. It's questions that evolve as your tools improve. That's what's happening now in the real future of Mars. We're shifting from simply exploring to preparing. Preparing for sample return. Preparing for deeper drilling. Preparing for the kind of testing that can't be done fully by robots alone. The most decisive step in the life question is bringing pieces of Mars back to Earth, into laboratories with instruments far more sensitive than anything we can safely drive around on a rover. A rock returned is a rock you can test and retest, a rock you can analyze with new methods decades later, a rock that becomes a permanent archive. That's why sample return matters. It turns Mars from a distant subject into something we can hold, study, and revisit as our science grows. And then there's the human side. The question of people going to Mars, not just machines. It's easy to romanticize, and you should be careful with that because romanticizing Mars is how we ended up believing in canals. The honest version is that Mars is dangerous. Thin air, radiation exposure, extreme cold, toxic dust, low pressure, and a world where every breath and every drop of water has to be engineered. Humans on Mars would live in habitats, behind shielding, relying on systems that must not fail. It wouldn't be a camping trip. It would be survival by design. But even that has a quiet beauty to it, because it forces precision and patience, qualities Mars has always demanded from us. If humans go, it will be because we learned how to bring warmth and air and water into a place that doesn't naturally offer them, and because we decided the knowledge is worth the effort. And beyond exploration and colonization talk, Mars also offers something simpler: perspective. When you think about a world that lost its easier water and air, you start to appreciate how fragile and rare Earth's balance might be. Not in a panic way, but in a grounded way. Mars becomes a reminder that atmospheres can thin, climates can change, and habitability is not a permanent guarantee. Mars is a before and after story. Earth is a living chapter still being written. So to round everything up, the story of Mars is a story of transformation. A world that formed from dust and heat, ran hot enough to build giants, held water long enough to carve channels and fill basins, then cooled and dried until water became ice and the sky became thin. A world that inspired war gods and omens, then inspired canal fantasies, then replaced fantasy with reality the moment our machines arrived. A world that keeps us coming back because it holds the closest, most readable record of a planet that might have been habitable and then changed. And if you're listening to this with the lights low, it's okay to let that story feel gentle instead of heavy, because Mars isn't asking you to solve it tonight. It's just there, circling the sun, turning slowly, wearing its rust-colored dust like a quiet cloak. Somewhere on that surface, the wind is moving grains of sand from one ripple to another. Somewhere at the poles, frost is growing or shrinking by the season. Somewhere beneath the ground, ice sits undisturbed, cold and patient. And above it all, the stars look sharp, because the sky is so thin, and the horizon feels far because the planet is wide and empty. Mars is a place where time feels visible. And that's a calming thing in the right moment, because it reminds you that your mind doesn't have to race. The universe moves without rushing. Planets change without drama. Questions can stay open without needing immediate answers. So as you settle deeper into sleep, you can imagine Mars not as a battlefield, not as a mystery you have to crack, but as a quiet, red world that keeps its history in layers, waiting, and you can let your thoughts slow down the same way the planet does, steady, patient, and calm, drifting gently through the dark.